All right, welcome back. In this video, we're going to go over a viewer-submitted question about Newman projections. So, I'm in a grand total of $0 in the past 28 days, and I added something different. So on the right-hand side, you'll see my Instagram. So go ahead, you can scan the QR code or type it in and follow me. And then you can DM me about any time about any questions regarding organic chemistry, physiology, biochemistry, anything like that, neuroscience, and I may respond. And if it's also good enough, I may actually make a video on it, just like this one. So we got two questions. One is about drawing the lowest energy conformation about Newman projections. And then the other one is drawing the bond line structure of Newman projections. So let's do it. For the first question, I actually made two videos on Newman projections, and they're actually doing really well. It's like one of two of my most viewed videos on my channel, which is great. So please go ahead and watch that. I'll link in the description. I'll put in the comments. So go ahead and watch that. It'll really help. But let's go over a few stuff. Here is a cheat code. This right here, honestly, if you know this, you're going to do really well on the exam. What this is saying is when you're given Newman projection problems, you're always given a perspective. Like, where am I viewing the molecule from? If the perspective is going from left to right, any functional groups that are on a wedge will appear on the right-hand side of the Newman projection, and any dashes will be on the left-hand side. And if perspective is going from right to left, then any dashes will appear on the right-hand side of the Newman projection, and wedges will be on the left-hand side. This is for normal Newman projections, not regarding energy conformations. Kind of. We're going to go over it. Now, energy conformations are basically other ways to draw Newman projections. It's basically how you organize the functional groups on the actual projection. And depending how it's organized, will show its energy conformation. So we have three different types of energy conformations. We have low, medium, and high. Let's do low first. This is also called the anti-conformation. This is when the bulkiest group from the front carbon that is attached to the front carbon is 180 degrees away from the bulkiest group on the back carbon. Okay, so remember the green part right here is the front carbon, and the yellowish looking is the back carbon. So the CH3 is the bulkiest from the front carbon, and the CH3 is the bulkiest group on the back carbon, and they're 180 degrees away. This is the anti-conformation, or the lowest energy state. This is because the bulkiness, they're not basically in each other's way, if that makes sense. They're completely far apart, as far away from each other as possible, that there's no interaction going on. That's why. Because when there's interaction happening, then there's energy being involved. Gauche is when they are 60 degrees away from each other, so right next to each other. Right? The Newman projection, like the actual geometry of it looks completely normal, like a normal Newman projection, right? They're just 60 degrees away from each other rather than being 180 degrees. This is a medium energy state, also known as gauche. Now, there's a different conformation now. This is called eclipse conformation. So whenever there are groups that are really close to each other like this is called eclipse. It's the highest energy state. This is basically saying that they're overlapping. So this is on top of this. So this group is on top of the other one. And it's basically causing so much interaction, there's so much energy there. That's what eclipse is. And you draw it a little bit differently. You notice it's not spaced out like this. It's more close together. So let's begin. Draw the following compound in the lowest energy Newman conformation. All right, so what do we do first? The first thing you do is identify where the perspective is. The I didn't draw the I this time, but the I is going from here, it's touching this carbon, and then touching this carbon, and then going off, right? So when this happens, it's like an invisible laser beam. It's this carbon first and this carbon second. When this happens, this is the front carbon, this is the back carbon, because whatever the arrow hits first is the front carbon, and whatever hits second is the back carbon, and we ignore everything else. So, we need to jot down, what are all the groups attached to the front carbon, okay? So, front carbon. Okay. Always, always, always there are three groups attached, never less, or never more. So, we start here, and we notice that we have a bromine, We have an invisible hydrogen that's on a dash here. And then we have a CH2 group, okay? We do not count this because that is going to the next carbon, right? This is going to the back carbon, so we don't count that. We ignore all this. Ignore it. Now, my viewer that sent this in said that this was actually a methyl group instead, because what she was doing is she was writing this down. She was doing this. Oops, CH3. That is correct. However, you need to include this carbon as well, because remember, we're looking from the perspective of this carbon. This carbon has a bromine attached, the hydrogen attached, and a CH2 attached, right? This is a CH2 right here, and this is a CH3. So we need to include all of this. So indeed, it's actually a CH2, CH3, a bromine, and a hydrogen that are all attached to the front carbon. Okay, even though there's a CH3 here, we need to include this one too because it's bonded. Eventually, it's bonded to this, right? So now we need to identify the back carbon stuff. Okay, so we look at here. This, we have a phenyl group. Now, if you don't know what a phenyl group is, let me draw it out for you. A phenyl group is this. That's really ugly, but it's basically a ring. That's what a phenyl group is. Really bulky, really, really bulky. It's a hint. So, we have a phenyl. Actually, first, let's do the actual bond line stuff. So we're looking here. We go down and go like this. So this is an ethyl group, another ethyl group. Even though we have a CH3 here, right? We do have a CH3 here. We have to include this carbon too. We cannot ignore it. Because remember, we're looking from this perspective of this carbon. So we go here and here. So this is a CH2 and a CH3. So this is a CH2, CH3. We have a phenyl. And then we have a hydrogen. That would be here. Okay. Okay. Now we identify where in the orientation it is on the Newman projection. So here's the trick. For the ethyl group, whatever's on the bond line structure, start from the carbon you're looking at. So we're looking at the front carbon. And you notice that we immediately go up, right? We go up. So the CH2 will be on the up position. And the bromine, since I said it's going to be on a wedge, right? So this is why this is really helpful. Perspective is going from left to right, right? So, right, the eye is we're going from left to right-hand side, right? The arrow is going from left to right. So that means anything on the wedge will be on the right-hand side. So the bromine will be on the right-hand side. And this would leave the hydrogen on the left because that's the only space that's open. Now the back carbon, the CH2, CH3, or ethyl, we start from the back carbon, and we notice we go immediately down, right? We're not going up, we're going immediately down, right? A downward slope. This tells us this is going to be in the down position. The phenyl is on a wedge, so that's going to be on the right. And then that means this has to be on the left, because that's the only space that's available. All right, so let's draw the Newman projection. So we do this. Actually, let me make it wider. Okay. So, actually, let me actually go slower than that. All right. So this is the front carbon. So we dictated, right? The front carbon's this, and then we have the groups coming off of it. So, in the up position is a CH2, CH3. So let me draw that in. CH2, CH3. On the right-hand side is a bromine. And then on the left is a hydrogen. Okay, now let's do the back carbon. And then in the down position is CH2, CH3. Actually, let me do it in a different color. In the right position is a phenyl, and left is a hydrogen. Okay, this would be the normal Newman projection. This would be the answer if you were just asked, just draw the Newman projection. But it's asking for the lowest energy. So what do we do? What you need to do is rotate the back carbon functional groups one space over, right? So one space over, and until you get the bulkiest groups 180 degrees away from each other. Because remember, the lowest energy conformation means that the bulkiest groups are 180 degrees from each other. So one's in the top position and the other one's in the bottom position. The question is, what are the bulkiest groups? So the bulkiest group from the front carbon, so the bulkiest group out of the CH2, bromine, or hydrogen is the ethyl group, CH2CH3. You might be thinking it was in the bromine because the bromine's on the right-hand side of the periodic table, right? It's like all the way on the right-hand side. Wouldn't that be the biggest? I see where you're coming from, but in terms of steric hindrance, it's the longest molecule. So that's the longest molecule, biggest molecule in terms of size. Like, think about like a train, right? This is 1 car length, this is 1 car length, this is 2 car lengths. So, right, because it's like 2 carbons. So think about like that way. So the bulkiest group is this. In the front carbon is this. The bulkiest group on the back carbon is the phenyl group. Compared to the CH2CH3, right? The phenyl, remember, is gigantic. It's like a huge ring. So it's super hindered, super sterically hindered. So that means the phenyl group and the CH3 need to be 180 degrees from each other. So how do you do it? All you need to do is redraw the Newman projection, but draw the phenyl group one position over, the CH2, CH3 one position over, and hydrogen one position over. So what do I mean by that is don't touch anything from the front carbon. Just move the phenyl group over here, move the CH2, CH3 over here, and move the hydrogen over here. So let me just erase this. So phenyl, this is CH2, CH3, and this is hydrogen. And this would be the answer. This is 180 degrees, right, from each other. Two largest groups are 180 degrees from each other. And that would be the answer. I'm pretty sure this is the answer. All right. Draw the bond line structure of this Newman projection. Okay, this is kind of a dumb question because of this. There's a gap here. Usually, when you're given Newman projections, you are told if this is either a hydrogen or a methyl group. I don't know, so I'm going to assume it's a hydrogen. But I think someone was lazy, or it's a typo because there should be something there, because it's kind of like it's kind of unfair, right? If you don't know what you know what's supposed to be, right? If there's a hydrogen, if hydrogen is literally written on the other pieces and it's missing here, right? Like I don't know what it could be. So draw the bond line structure of this Newman projection. All right, so what do you do? All right, so first step is identify what's connected to the front carbons and the back carbons. So same thing as usual. Front carbon. We have hydrogen, right? Because I'm looking at stuff that is part of the cross here, right? This is the front carbon stuff. We have a bromine, and then we have this super weird squiggly line stuff here. So this is CH2, 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 CH3. So CH2, 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 CH3. Okay. Yeah. And then the back carbon stuff, so back carbon. This is anything in the circle. So we have a fluorine, hydrogen, hydrogen. So hydrogen, fluorine, and hydrogen, right? Yes. Okay. Now we need to identify what is in what position, right? Because we need to know what, if there's any wedges or dashes, what it's going to be on, right? So bromine is on the right-hand side. on the front carbon, right? So this is the Newman projection, right? Bromine's on the right-hand side. So this means it's going to be on a wedge. This is assuming that the perspective is going from left to right, right? Like that way. I don't know. It's not given to us. So I'm just going to assume it is. That's why I also said it's kind of a bad problem. Right. Yeah. No, sorry, wedge. That means that the CH2, 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 CH3, all this crap right here, this is on the left-hand side, so this means it's on a dash, because remember, this stuff, right? Perspective, wedges on the right, dashes on the left. Since the CH2, CH2, CH3, CH3 is on the left-hand side, it's going to be on a dash. The hydrogen's pointing up, so this is going to be in the up position. Let's do the back carbon stuff. The hydrogen is pointing down, and then, so this is pointing down. The fluorine is on the left-hand side. However, we have two of the same groups here. Right, so we have a hydrogen here and a hydrogen here. Two of the same groups attached to the back carbon. This means it's not chiral. This also means there are no wedges and dashes on the back carbon. If you have two of the same functional groups attached to the carbon, that means there's no wedges or dashes. So you don't need to draw them in. So we don't really actually care. So what does this mean? So how do we draw this? So we draw this by... So we have hydrogen up position, right? So we first gonna draw the carbon, the front carbon, the back carbon, like this, right? The reason I'm drawing this is because we need something like this for the hydrogen here. Okay, so this is gonna be the front carbon. So let's just call this F for front carbon and B for back carbon. Okay, let's do it like that. So just draw the line first. And then since the hydrogen is in up position, we need to make sure we go up from here. So from the front carbon, we have to make sure we go up. So we did that, and the bromine's on a wedge. Is on a wedge. So let me draw that in. Like that. And then CH2, 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 CH3 is on dash. So actually, let me move this over here. So dash. Okay. So and all you have to do basically is just draw this. Just draw that. So let me draw that in. Just copy and paste, kind of. CH2, 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 CH3. Okay. Yeah. And then we do the back carbon stuff. The back carbon, the hydrogen's pointing down. So we go down from here. Hydrogen. And then, so now we have the fluorine and the hydrogen. Remember, there's no wedges or dashes. So all you have to do is just draw the fluorine here. And then if you want, you can draw the hydrogen. You don't have to. But that would be the answer. This is how you would draw the bond line structure of this Newman projection. So if you found this video helpful, please like and subscribe. Until next time, later.